All right. Good afternoon, everyone. As you guys all know, the midterm will be on Wednesday, I believe, since midterm should be on 11th. So, for practice material, I'm going to be going over solving the midterm one practice exam live on video. So, I think generally speaking, from my past experience in the course, the past practice exams are very good indicators of what you can expect on the midterm. Topics are very similar, and what you need to know and what you need to know, such like the important contents and whatnot, it's all very similar. So I believe that going over, like, say, the first practice exam, not only that would be able to adeptly prepare you to solve other practice midterms, which are all very similar in topics. And so, without further ado, let's begin. So, typically, with the first midterms, what you're all going to begin with is constructing truth tables and checking the logical equivalence and basic propositional logic and stuff. And just as a quick reminder, these should just all be freebies, by the way. So construct a truth table of the following form. So we have three variables. Let's do this as P, Q, R. Let's give ourselves a little bit more space. So P, Q, R. And since there are three variables, we have 2 to the third equals to 8 possible rows. So 1, 2, 3, 4, 5, 6, 7, 8. So if you remember, we first began by alternating 2 to the second values, 2 to the first number of values, then 2 to the 0 number of values, or alternating every 4 between truth and false, every 2 between truth and false for a second column, and then every once. So how that looks like is going to be like this: true, 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 for 4 truths, 4 falses. F, 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 F. Q would then be alternating every 2 times. So true, true, false, false, true, true, false, false. And similarly for this, true, false, true, false, true, false, true, false. And then we begin to work from the first operation up until the outermost operation. So the first one is going to be P or R. So P or R, as you recall, the truth table for OR is that if one of them is true, then P or R is true. So this is true, 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 true. FF is false, true, and false for the last one. So that was P or R taken care of. Now we can go into P and Q or R. And essentially it is this row and this row. So this will be true, 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 false. Oh, sorry, this one should be false. This one should be false. So then in this case, this one is false, 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 false. Then we can move into the second part of the conditional, which is P and R. So P and R, and is when both values are true. So only if both values of the here are true, then P and R is true. So we have true, false, true, false, 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 and false. Now we can move on to ultimately the final column, which is our entire thing. So it is this column. For the sake of writing, let's call this A, and then let's call this B. So if A, then B. And for the conditional, if we recall, the conditional is only false if it is in the form of true, then false. So true, then false would result in false. Otherwise, everything else is true. So this is true, true. This is true, false, true, 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 and true. And there we have it. That's the answer for number 1. All right, so now we can move on into checking the logical equivalence. And checking the logical equivalence is relatively simple, similar in idea, in that you still construct the truth tables for each of these statements. But the key here is now you have to pay attention to every row of this. Say you have some statement of B, A, some statement B, then A is logically equivalent to B if and only if every row in the truth table, the value is true. So let's see how this works in practice. Let's give this again a lot more space. Once again, we have P, Q, R. We have 2 to the third equals to 8 rows. So 1, 2, 3, 4, 5, 6, 7, 8. So once again, true, 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 false, 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 true, true, false, false, true, true, false, 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 true, false, true, false, true, false, true, false. Okay, and so then we have P and Q. P and Q should give you true, true, false, false, and everything else should be false. And then we have P and Q implies R, which is one of the row values we're trying to find. So then we have P and Q implies R. So true implies true, true, true implies false is false, false implies whatever the hell this was. This is a true. But regardless, since the first value is a false, we know this is true, 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 true. And now we can move on to the second bar. So we have P implies R. P implies R, true, false, true, false, true, 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 true. And also Q implies R. So we have Q implies R, true, false, true, 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 false, true, true. So now we have this row or this row. So in this case, we have true or true is true, false or false is false, true, 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 and true. And this is this part. So now we consider all the values in these columns and check if every corresponding row lines up. So this is true, true, false, false, true, 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 and true, true. So in this case, since every row lines up, this is logically equivalent. All right, so that's number 2. Number 3, give negations of the following statements. Reasoning is not required. So once again, basic propositional logic concepts, negating, knowing how to negate. So again, one of the most important concepts, especially regarding and or statements. Sorry, that was a tongue twister. Is De Morgan's laws, which so suppose you have some P and Q and P or Q, then the negation of P and Q is equal to not P or not Q. And the negation of P or Q is equal to negation of P and the negation of Q. So essentially what you're doing is that you're distributing out the P and Q into the negation and then flipping whatever this is. So if it's an and, flip it into or. If this is an or, flip it into and. So that alone allows us to solve the first two very straightforward. So P and Q, negation of P or negation of Q. Similarly, this can be written as negation of P and negation of Q. And these two are just De Morgan's laws. Okay, so next we move into something slightly more involved. And what this is the exclusive OR connective. So exclusive OR is different from the or in that the or only needs one of them to be true. But an exclusive or, one of the two between P and Q has to be true, and the other one has to be false for it to be true. So the truth table of the exclusive or is given as follows. So we have some uh, P, Q, P exclusive or, this is or Q. So we have true, true, false, false, true, false, true, false. And so true and true actually gives false. True and false gives true. Uh, false and true gives true, and false gives false. So in this case, it takes some trial and error to see what gives Q XOR P XOR Q. And so you think about it and you're like, okay, P XOR Q is only true if one of them is true and the other one is false. So that gives you alone some intuition which to build what an equivalent expression to P XOR Q is. And if we could then apply De Morgan's laws into the form of like and or statements, say if we could transform the XOR statements into the form of and or statements, then we can apply De Morgan's laws to negate them. So let's see. So one of them has to be true. So there are two possible outcomes in which P is true and Q is false, or P is false and Q is true. So then in this case, we can equivalent write P XOR Q is logically equivalent to P and not Q, or P or not P and Q. Because or indicates the two possibilities that only one of them is true, which is why we use an and to represent one of the variables being true and the other one's being false. So then in this case, we see that we have it in terms of or, ands, and ors. So now we can apply De Morgan's laws. So to negate this, we flip both sides of the operand. So then the negation of P XOR Q then becomes not P and not Q, flip or into an and, not P and Q. And I would generally say it's probably okay to leave it like this if you're like on exam, especially when time matters and you have to like finish within time. Leaving it like this is okay, but you could probably apply one more step to of De Morgan's laws to this to transform this to transform these two parts, recognizing that this is negating an and statement. So then this would be distributing out the p into the negation, not p, flipping this into an or, not p or q, and so negations cancel out here, p or not q. And this is your answer for part C. Don't worry about me erasing the answers. I will post the document containing all the answers to practice midterm on Ricebase. So now we go into negating the conditional. And negating the conditional, once again, is fairly straightforward in that to negate the conditional, all you have to do is negate the second part of the operand. So this one is also very easy, as this is just P implies not Q. Q. This is how you draw the Q. Okay, so that one's very straightforward. But what about the biconditional? So the biconditional truth table is as follows. The biconditional is true when wait, give me 1 second. P Q T T T T T F T F. So the biconditional is only true when both operands are equal. So that means that there's no true by vacuous truth. So there's no vacuous truth. Vacuous truth is when false implies true. So in this case, it is essentially the same thing as the conditional, except this condition is false. So in this case, the truth table looks as follows. So true is true, true false is false. Wait. So false implies true is actually false because there's no vacuous truth in the in an if and only if. And P implies Q, false is true. So once again, we can aim to translate this into and or statements so that we can utilize the Morgan's laws. So once again, so the only two possibilities in which these two are true is if they're both so either both are true or both are not true. So we can rewrite this as follows: either P and Q or not P and Q. By the way, on exam, I know this is all kind of hand wavy and that it seems like I just pulled out of my ass, but like on exam, you gotta like recognize, okay, what values make these true and what values make these false, and is there some expression I can construct such that they will be logically equivalent? And on exam, I would recommend you guys use a truth table just to verify that this statement is indeed logically equivalent to whatever you're deriving for. In this case, it is. Just take my word for it, since I'm trying to go through the exam for the interest of time. So once again, we have this in and or statement. So once again, apply de Morgan's laws. We have negation of P and Q and the negation of not P and not Q. Once again, you can leave it like this or apply de Morgan's laws one step further into not P or not Q or wait, sorry, and because in this case we're negating these two operands, not this. So and P or Q, and that would be our answer for that part for the biconditional. Now we move on to negating existentials and universal quantifiers. And I could explain the logics of this once again, but really the most ironclad rule you need to know is for if you have an existential quantifier, say for all x, blah blah blah, p of x, flip this into into an existential. There exists an x such, and then negate whatever follows after. And similarly, for an existential, you negate this back into for all x not P of X if you have there exists an X such that P of X. So once again, flip whatever comes first, negate what comes after. So once again, for all x, there such that for all y, such that p of xy. So first, what we have to do is flip this into an existential. There exists an x, and then negate whatever comes after that. So now we are negating this part. So for all y, then we negate this into an existential. Now we negate this part, such that p of xy, then we can write not p of xy. And that's all we have to do. Once again, apply the same principle for g. Negate this into an existential. There exists an x. Negate this into a universal. And now negate p of xy such that not p of xy. And I'm just going to speed run this so you guys see what it's like. For all x, there exists a y such that p of xy is false. Or you just write not. And once again, for all x, for all y, such that not p of xy. And once again, I know there's three, but once again, don't panic. Negate this first into a universal. Negate this one into an existential. Negate this one into a universal. And now negate p of xyz. So such that not p of xyz. And that's all for negating. So now we move into logical inferences or deductions, or logical deductions, inferences, whatnot. So determine if the following deduction rule is valid. P implies Q, Q implies R. So does P implies R in this case? Well, if you remember from the table of logical rules that you can use in inferences, this is indeed true, and this is called transitivity. Transitivity. So if you just memorize that from the book, awesome. That might be able to save you a question worth of time and just directly say, okay, this is true by transitivity. Let's move on to number 5. So, the other way to do this is to construct a truth table. Truth table. And find the truth values of all these statements in the truth table, and consider rows in which all the predicates are true. And if there's one row in which the conclusion is false, then that means that the deduction is invalid. But if every single row having the predicates as true has the conclusion as true, then the deduction rule is true. So for the sake of demonstrating that, and in the interest of time, I'm not going to do that for 4, because 4 is once again, if you recall transitivity, you can directly say that. And I think I'm going to make a document of important midterm information to know, and I'm going to attach that into the document. So if you guys want to study that, then yeah. But let's see how it's done for number 5. Since number 5, there's no straightforward rule for this, at least not that I remember. So we have P implies Q or R, not P implies Q, so we conclude that R must be true. Now, is that valid? Let's construct a truth table for this. So P, Q, R. I should probably give myself more space. So we have P, Q, R. Once again, true, 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 false, 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 true, true, false, false, true, true, false, false, true, false, true, false, true, false, true, false. And so to construct P implies Q or R, we need Q or R first. So in this case is true, 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 false, true, 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 false. And so then P implies Q or R is this column implies this column. So true, 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 false, true, 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 true. So then we have not P implies Q. And so is whatever is not this row implies this row. So true implies true is true, but we negate that into false. This one is also false. True implies false gets negated into true. And this one also gets negated into true. And every other line gets negated into false. So false, 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 false. And so we consider every row in which P implies Q or R is true, and not P implies Q is true. So we're looking for all rows in which these two are both true. So it's not this row. So all we are considering is this row. Now, is our conclusion that R must be true valid in this case? Well, if we look at the row, there's only one row, and R is true in this row. So that means that in this case, this argument is valid. Now, there might be also questions that come up in the case of, okay, what if I have multiple rows in which my predicates are true, and these are called the critical rows. So what if, say, also this one, let's just pretend like this one is also true. And R is also true in this case, fine. Okay, oops, terrible example. But let's say also this row, let's pretend this is also true. Let's pretend this is true. So we have true, true, but now we have one row in which R is false. So if you conclude R, then this is an invalid argument because we have one row in which our conclusion is false, but all my predicates are true. So just to demonstrate as an example of how to prove validity in logical inferences. Okay, so now we move on to proofs. And proofs, once again, there are, I think what are most important to know are direct proofs. And proof by contradiction. Once again, with direct proofs, you can refer back to previous recitation materials for direct proofs and relevant information. Once again, you have proof by construction, or proof by example, or counter example. And construction is used for universal styles of statements, such as for all integers, for all. And the keyword really is for all. And example or counterexample are for existential statements. And counterexample is the specific name given for proving the negation of a universal, proving that a universal is not true. And that is counterexample because the negation of a universal is an existential. So example or counterexample is used for existential statements that we want to prove. So let's take a look at problem number 6 on the midterm. So prove or disprove the following statements. For all integers, now we know that for all, since we're trying to prove, actually it says prove or disprove. So for all integers, if a is odd, then a to the fourth is odd. Intuitively speaking, if you think about it, an odd number times an odd number is always an odd number. So then it doesn't matter. It shouldn't matter how many times you multiply. So let's try to actually prove this. So if we try to prove this, we're trying to prove a universal. So let's try to do it by construction. So let's have proof. Suppose we have some integer a such that a can be represented as 2k plus 1 for some integer k. Then a to the fourth is equal to 2k plus 1 to the fourth. And do some algebraic math, then you end up with 2k plus 1 to the fourth is equal to what should we call it? This should be equal to 16k to the fourth plus 32k to the third plus 24k squared plus 8k plus 1. Okay, and we've gotten what this is, but this is still kind of cryptic, and we want to know whether or not this is odd or even. So intuitively speaking, we should be trying to factor out a 2 somewhere. So all the even coefficients can have a 2 taken out of it. So then this is equal to 2 times k to the fourth plus 16k squared, k cubed plus 12k squared plus 4k plus 1. So now we have this in the form of some integer in terms of k times 2 plus 1. And we now know that this is in the form of an odd integer. But we still have to explicitly say that in our proof, because in proofs we want to be extra clear so that we don't get points taken off for ambiguity or such. So then we can say let j be some integer in this form, such that j is equal to k to the whatever this quantity is. Then we can see that a to the fourth equals to this equals to 2j plus 1, which since j is an integer, this is in the form of an odd number. So then we can conclusion that a to the fourth is indeed an odd number. So that would be how you would be proven direct proof by construction. Alternatively, you can try to solve this with congruence classes. However, note that since congruence classes have not been taught yet, to use any arithmetic properties of congruence classes, you have to prove them. So with congruence classes, we are given that the congruence class of A mod n times the congruence class of B mod n is equal to the congruence class of AB mod n. But now we have to prove that if we want to use it, because if we think about it, then the congruence class of A to the fourth mod 2 is then just equal to, since the congruence class of A mod 2 equal to 1, since we know that it's an odd integer, then this is the same thing as saying 1 to the fourth mod 2, which is equal to 1 mod 2 multiplied 4 times, which is just congruence class of 1 mod 2, which gives us the answer that this is an odd number. So now we have to prove that given some x and y, if we multiply them, this is the same thing as xy mod n congruence class. And how you would do that is you would prove that since x represents the set of all numbers, let's say p is an element of the congruence class of x mod n. So p is equal to nk plus x for some k, and q is equal to nl plus y for some l. And remember, the congruence class of x is a set of all numbers that give the remainder of x when divided by n. So then we can write PQ is equal to NK plus X times NL plus Y. This is equal to KLN squared plus NKY plus NLX plus XY, which is the same thing as if we factor out an N from the terms. This is KLN plus KY plus LX times N plus XY, which gives us an a number that since we have an integer times an n with the remainder of xy, which gives us a number that has a remainder of xy when divided by n. And what you have to recognize here is that xy, there might be parts of xy that can be absorbed into n, but and that is basically kind of how congruence classes work. Different congruence classes are equal to each other. Say the congruence class of uh, 1 mod 2 is congruent to the congruence class of 3 mod 2. And that is because, like, again, 3 mod 2 gives the same remainder as 1 mod 2. So again, congruence classes work like that. So once you have this proof, then you can say, okay, a to the fourth mod 2 is just the same thing as a times a times a times a. But since this is all 1, then this is just the congruence class of 1 mod 2, which shows that a to the fourth is odd. And that would be how you would do it. But once again, if you're using anything that is outside the knowledge of the class, be sure to prove it first so that you can use it, so that you don't get points taken off. Next, we move on to 7. So we have to prove or disprove the following statement. The difference of two perfect squares is not a prime number. Here's the reasoning for this claim. So it's saying, sorry, a squared minus b squared is equal to a plus b, a minus b. Difference of squares factorization, which is a composite number because it has two factors, right? It's divisible by some number, so this is composite. So once again, we remind the definition of a prime number is a number that only has 1 and itself as its divisors. So from the definition, we can directly see that, okay, if a plus b or a minus b is 1, then this is clearly not a prime number. And we're mainly looking at a minus b because 1 is most likely less than itself. I don't think any negative numbers are considered prime numbers. So we're looking at all positive numbers that are prime, all positive numbers in the domain of prime numbers. And in this case, okay, we say, what if a minus b is 1? So then we can consider, okay, let's say let a equal to 3 and let b equal to 2. Then 3 squared minus 2 squared is equal to 5, which is indeed a prime number. Oh, and don't forget to put proof a counter example. And therefore, the conclusion is that the claim is false by counter example. Because we found an example of a difference of squares, which is a prime number, which is the direct negation of the claim itself. And so the negation of the claim is true, which must mean the original claim is false. Therefore, we conclude that the claim is false by counterexample. Now we move on to proof by contradiction, that there are no integers x and y such that x squared is equal to 4y by 2, 4y plus 2. And proof by contradiction, as a brief reminder, works as follows. So suppose the negation of the claim. If you can show that the negation is obviously false, then the negation of the negation or the original statement must be true. And that's how you prove by contradiction. So let's see, prove by contradiction that there are no integers x and y such that x squared is equal to 4y plus 2. And they give us a hint. For this problem, you can assume without giving proof that if x squared is even, then x is even. So proof by contradiction. So then you begin by supposing the negation of the claim. So there are no integers x and y such that x squared is equal to 4y plus 2. So suppose there is some integer x and y such that x squared is equal to 4y plus 2. Wait. Yeah. So suppose that there is some integer xy such that x squared is equal to 4y plus 2. Uh, Now, observation 4y plus 2 is even. And you can do this by proving it with congruence classes. So this is the same thing as a congruence class of 4 mod 2 times the congruence class of y mod 2 plus the congruence class of 2 mod 2. And since the congruence class of 4 mod 2 is 0 mod 2, since 4 divided by 2 gives a remainder of 0, then uh, the congruence class of this is equal to the congruence class of 0 mod 2. So that shows that 4y plus 2 is even. Observation 4y plus 2 is even. So this implies that x squared is also even. If x squared is also even, then that means x must be even. Um, from the hint, which is a relatively obvious hint, but like since the problem said you didn't have to prove it, you don't have to prove it. But in an actual problem where they don't say that, any assumption you say, such as x squared is also even, then that means x must be even. You must include a subproof of that in your answer. So in this case, we're given that we can just assume this. So that means x must also be even. Then x must then x can be expressed in the form of x equals to 2k for some integer k. Then that means that x squared must equal to 2k squared is equal to 4k squared, indicating that x squared must be a perfect multiple of 4. But we are given in the original definition that says x squared is equal to 4y plus 2, which is saying that x squared is not a perfect multiple of 4. It gives a remainder of 2. This is a contradiction. Therefore, the original claim that there are no xy's such that x squared is equal to 4y plus 2 is true. And that is our proof by contradiction. So begin by supposing the negation. Suppose there is some integer xy such that x squared is equal to 4y plus 2. And here is where you have to get a little creative. Notice some properties about the claim. So in this case, the hint is a very strong hint too. You can assume that if x squared is even, then x is even. So it revolves around the parity of the numbers. And you can notice then that, okay, so if x squared is even, that means 4y plus 2 must be even, right? And in this case, the form of 4y plus 2 means that this is always an even number and can never be an odd number. So the only case we have to consider is if it is even. So observe that this is even, then x squared is even, so x is also even. Now, from the definition of our observations, if x is even, then x squared must equal to 4k squared, which then we can conclude that, okay, if we suppose the negation of the statement, then that means that it must be a perfect multiple of 4. But this directly goes against our, supposed, so the definition directly goes against our supposed claim, which shows a contradiction. And therefore, if our supposed statement is false, and our supposed statement is negation of the claim, then that means that the claim must be true. And that is proof by contradiction in a nutshell. In any case, this is basically it for practice midterm 1, I believe. 8 questions. Again, the most I believe that the practice midterms are very indicative of what topics you're likely to see on the midterm. So definitely know how to construct truth tables. These are such free points. So definitely know how to construct truth tables. Um, because uh like most of the class will be able to do that. So you don't want to miss out on any points that most of the class is going to get. So truth tables, basic logical operators and their relationships, truth tables of or and statements, and also do not forget about some of the more elusive ones such as the XOR or the biconditional. And how to draw their truth tables and how to derive relationships, how to negate existential and universal quantifiers, how to say uh, determine whether logical arguments are valid or invalid. And remember, this is by critical rows. So that's problem 4 and 5. Critical rows of a truth table. Then you definitely need to know how to do proof by direct proof, which includes proof by construction and proof by counterexample or example. And also proof by these are proof by construction and counterexample. And finally, proof by contradiction. Expect to see one problem or so on it, which is probably going to be the hardest problem that you're given on this exam. But again, maybe you'll get a hint that can get you points, get you like towards the right track in solving the problem. But if not, once again, start by supposing the negation of the claim, and just really use your creativity, see what you can construct out of it. And honestly, none of these are going to be impossible problems. So if you think you have a right idea, go for it. Try to directly show that the supposition is absolutely false. And yeah, that's basically all for this practice midterm.